So we as lab persons, we are not involved in clinical research. We just can adopt the findings from the clinical colleagues, but we can somehow state some correlations. We need first to simplify the clinical situations where you have a variety of patients of different age, of different patterns. There are so many variables that we need to simplify the problem. This is what is the first step in the lab. So from a field test, a private dental practice places a lot of fillings and somehow he gets a response after years if they are still in service or not. Then there is a controlled clinical study which limits the variables for a clinical statement. But then you need to go to the lab. For example, you use a chewing simulator where you use two antagonist tools moving together, loading each other, and then you can make some statements for the clinical situation. This is more standardized, but coming to a more simplified geometry with a flat specimen and a ball, for example, or even the easiest way is to use these bars for measuring just one parameter. And with measuring this one parameter and finding some correlations, then you can make some conclusions to the clinical situation. This is what we do. Very easy. You might know that the bending can be in 3-pointing or in 4-point bending. This is quite common, I think, to everybody. And you can measure the strength. This is what you find in every instruction for use. If you buy a material and they say, we have a strength of 100 megapascal. They tell you this value and is measured according to ISO standards and so on. But in order to be clinically relevant for a long-term perspective, you need to go somewhere in a direction for a cyclic loading, which is more clinically relevant. And I would like to go this way now. So basically, the dynamic loading, the cyclic loading can be in different ways. It can be in tension, it can be in compression. And once we look for our chewing patterns, of course, we are in the compression field. And in the compression, we see that the lower level for the stress is 0. So this is the open mouth, and then we choose. So this is the situation which is interesting for us. We have 0 to a certain stress amplitude, a certain level where we load, and this is in a cyclic with a physiological frequency in a cyclic way. So coming from the initial fracture, the initial loading, fracture strength, we reduce the stress amplitude to 80%, to 60%, 40%, and so on, 20%. And we will find that a material survives more cycles the more I reduce the stress amplitude. This gives an indication what happens during cyclic loading. We used water as the environment, which is close to the clinical situation. We use a frequency, which is close to mastication frequency. And then we get a behavior which is more or less like this. Beginning from the initial strength, the more cycles we apply, the less strength will withstand the material. And this we have done. For example, here are 1 million cycles, and you see for a resin composite we measured 100 megapascal in the beginning, and it drops down to 20 megapascal after 1 million cycles. This is a test which takes a long time. 1 million cycles at 2 Hertz, that takes you weeks and months of experimental work. So we decided to focus on a window in this so-called Wöhler approach. We decided to focus on a window, and we chose 10,000 cycles as a reference for us, and we measure the stress amplitude, the stress we can expect after 10,000 cycles. This is much easier and much more economic in terms of time. This is the so-called staircase method. We use more specimens, 20, 25 specimens. We start with the first one, and we give it a stress amplitude. We see if it fails or if it survives, and then if it survives, we increase the stress amplitude. If it survives, we further increase the stress amplitude until it fails, then we reduce, we increase. And with this step-by-step measurement of, 25, 30 specimens, we get a so-called staircase profile where we can calculate statistically kind of fatigue limit, which has a limitation for 10,000 cycles. This is just the value which gives you an idea what happens under cyclic loading conditions. So not the whole Wöhler approach, which takes you a long time. It's just a simple value which gives you an indication of how good is a material and how bad. This is what we have done. This is a number of materials on the market. You see there are values from 120 down to below 80 megapascal for the fracture strength. And if we measure this staircase fatigue, then we see that the strength drops a lot. We can calculate the percentage, and we see there are materials which are really resistant to cyclic loading. They only drop for 35%, or there are others which drop almost 60%. So there are differences. And we try to question where are these differences coming from. So what we did is, here is water storage. We measured fracture. We measured our fatigue limit after time. So we have seen there is 1 day versus 90 days, so 3 months of water storage. And we see the strength of a resin composite drops with a longer water storage. So there is something happening just coming from the water, but not in terms of fatigue. A resin composite is somehow stable in terms of cyclic loading. It's different here. The green curve is for a glass ionomer cement. This is just to point out that the glass ionomer in the long term seems to be a more and more stable material in terms of fatigue. So we further questioned what happens. We see a strength which drops after water storage. We have done a test. These 4 bars are different light curing times. Light curing means, for example, 20 seconds, 40 seconds, 60 seconds, 240 seconds of light curing, which should somehow represent a different degree of conversion. So after 1 day, you get a better strength with a longer curing time. This is very well known, but after 90 days, it's somehow equal. The strength of the material is somehow equal, respectively, not depending on the light curing time. Then we measured the water sorption, and again, we see after 1 day, the material with a better curing does not absorb the water as does a specimen which is only cured for 20 specimens. But again, after 90 days, all the specimens have taken up the same amount of water, so they somehow equaled at a certain level. Then we measured, after the strength, we measured the fatigue of these materials. Something is missing. Well, actually there's a graph missing, which shows the fatigue of this material, and this is a pity that it's missing. Because under fatigue conditions, the material does not follow the same development as it does under fracture strength conditions. Means after 1 day, it looks like this one here, but after 90 days, it looks the same. There's also a trend that the materials with 20-second curing, they have the lower mechanical resistance compared to the material with the 240 seconds. This gave us an indication that there's something happening related to the water uptake in the material. The water is coming from the surface. This is a diffusion controlled process in the inner parts of the material, and the strength is mainly related to the surface properties of a specimen, to a material, and the fatigue itself is a property which is more related to the bulk properties of a material. So it's, there is a difference between strength and fatigue. There is a reduction, we see a reduction in fatigue strength, but the same trend within the groups. So we see the best fatigue resistance for 240 seconds curing and the lowest resistance for 20 seconds curing, also after 90 days, irrespectively of water uptake. So we further did a simple test. We wanted to question what happens because initial testing is a very quick test. You put the specimen in the machine and fracture, and the cyclic loading is a very slow test. So we just looked at what happens in a stress-strain plot if we apply a very quick, a very fast loading rate compared to a slower loading rate. And you see the material, once you give it, the resin composite, once you give it some time, it somehow has a higher strain and a higher potential for deformation compared to a material that is loaded very quickly. And this has also been done by others. So you see there's the time dependence of stress and strain. And once you apply a stress and you keep it constant for a time, you see the material with the strain follows in a certain curve, which in the beginning is characterized by elastic properties, elastic modulus. But over time, if we keep the stress constant, it's more the viscous part of the material which becomes prominent, and the material starts creeping and deforming. So this is a difference between fast fracture and slow cyclic loading. Then, with this knowledge about the differences of between fast and slow fracture, let's say in that way, strength and fatigue, we try to find some differences at fractured surfaces. You could do that from clinical specimens, from clinically failed restorations. You could do that also from lab specimens. This is what we did, but this is in vivo, and we did some in vitro fractographic examinations on fracture surfaces. So, well, in principle, a fracture somewhere starts, there is an origin, and it develops into the material coming up at the other side of let's say, a specimen or of a restoration, where there is always this compression curl with it's a zone of compressive stresses. Well, but we see this kind of mirror developing from the origin in all directions, where is the easiest and best way for a crack to develop through a material. So we see some patterns, and we put our initial fracture strength pattern specimens under the microscope, and we clearly see that there is an origin developing in the different directions of the specimen, ending up in the compression zone. If we now put a fatigue specimen under the microscope, we have a totally different appearance, where we don't see, in the first step, we don't see anything. This is a very smooth and flat fractographic appearance. So there is a difference in terms of energy released by the fracture process. There's much more. This is a rough appearance, this is a smooth appearance. If we go deeper into the microstructure of the materials, these are both the same materials, of course. If we go deeper into the microstructure, we don't see any differences. So we try to question, is there any difference, or where is the difference coming from? Is it on a macroscopic level? Is it on a microscopic level? Do we need to look closer to the fracture surfaces? Is that necessary, or do we better focus on the macroscopic patterns?